It was 4 days before Christmas, 1938, inside a cold, dimly lit laboratory at the Kaiser Wilhelm Institute in Berlin. A 60-year-old German chemist named Otto Hahn was staring at results that made absolutely no sense. He had been firing neutrons at uranium atoms for weeks, not to build a weapon, not to end a war, not to reshape the fate of civilization. He was simply trying to create new, heavier elements. It was routine science, careful, methodical, unremarkable. And then the results came back, and everything he understood about the physical world collapsed into rubble. The uranium had not become heavier, it had split in two. It had produced barium, an element with roughly half the mass of uranium. That was not supposed to be possible. It was, in the language of physics, preposterous. Hahn himself wrote to his exiled colleague, Lise Meitner in Sweden, barely able to believe his own findings, saying something to the effect that the results were so extraordinary he could not bring himself to fully accept what they meant. He submitted his paper to the scientific journal Naturwissenschaften on the 22nd of December 1938 without a complete explanation, because no complete explanation existed yet. He had accidentally split the atom, and he had absolutely no idea what he had just done to the world. This is the story of the most terrifying, beautiful mistake in human history. The atom itself is ancient beyond imagination. Uranium, the element at the center of this story, was forged inside dying stars billions of years before the Earth existed. It arrived here embedded in rock, dense and radioactive, leaking energy slowly across geological time. For most of human history, nobody knew it existed. Then, in 1789, a German chemist named Martin Heinrich Klaproth isolated it from a mineral called pitchblende and named it after the planet Uranus, discovered just 8 years earlier. For over a century, it sat in the periodic table, heavy, mysterious, and seemingly inert beyond its gentle radioactivity. Scientists probed it, they measured it, they bombarded it with particles, and in every experiment, it behaved. Until the night Hahn and his colleague Fritz Strassmann found that it did not. What Hahn had stumbled onto was nuclear fission. When a slow-moving neutron strikes the nucleus of a uranium-235 atom, the nucleus becomes unstable and splits apart violently, releasing two smaller atoms, several free neutrons, and an almost incomprehensible burst of energy. Those free neutrons then strike neighboring uranium atoms, splitting them in turn, releasing more neutrons, which split more atoms in a chain reaction that builds with exponential speed. The energy released by a single kilogram of uranium-235 undergoing complete fission is equivalent to burning approximately 3 million kilograms of coal. This is not a metaphor. This is the mathematics of destruction hiding inside a piece of silvery metal that fits in the palm of your hand. It was Lise Meitner, Hahn's longtime collaborator and one of the most brilliant physicists of the 20th century, who first understood what Hahn's chemical results truly meant. Sitting in a snowy Swedish forest on a winter walk with her nephew Otto Frisch, she worked through the calculations on a scrap of paper using Einstein's equation, E equals mc squared, as her guide. The numbers were staggering. The energy released when a uranium nucleus split was millions of times greater than any chemical reaction ever recorded. Meitner and Frisch published their theoretical explanation in the journal Nature in February 1939. Frisch borrowed a term from biology, the process by which cells divide, and named the phenomenon fission. The world of physics would never be the same, and neither would the world itself. Word spread through the scientific community with terrifying speed. In America, physicists Leo Szilard and Enrico Fermi understood immediately what a chain reaction of uranium fission could mean in the hands of Nazi Germany. Szilard, a Hungarian Jewish refugee, who had already dreamed theoretically of a nuclear chain reaction years earlier, was alarmed enough to sit down with Albert Einstein and draft one of the most consequential letters in the history of warfare. The Einstein letter, delivered to President Franklin Roosevelt in October 1939, warned plainly that uranium could be used to build bombs of enormous destructive power, and that Germany might already be working on it. Roosevelt responded, and what followed was a secret so large that Vice President Harry Truman himself had never heard of it until he became president. The Manhattan Project officially launched in August 1942. With over 30 project sites and over 100,000 workers, the Manhattan Project came to cost approximately $2.2 billion. In today's money, that figure exceeds $30 billion, the most expensive single weapons program in human history at that point, funded in secret, hidden from Congress, buried in War Department appropriations that nobody questioned because Roosevelt had promised that if it worked, no one ever would. The scientific firepower assembled under the project was extraordinary. J. Robert Oppenheimer led the weapons laboratory at Los Alamos, New Mexico. Enrico Fermi and Leo Szilard built the first self-sustaining nuclear reactor beneath the squash courts at the University of Chicago in December 1942, a reaction that produced only enough energy to power a light bulb, but which gave scientists a working model for the production of plutonium on massive scale. Glenn Seaborg isolated plutonium in sufficient quantities to construct a second type of bomb. Hans Bethe ran theoretical calculations. Thousands of other workers, engineers, machinists, chemists, labored across the country, most of them not knowing what they were building or why. On July 16, 1945, at Trinity site near Alamogordo, New Mexico, scientists readied themselves to watch the detonation of the world's first atomic bomb. A blinding flash visible for 200 miles lit up the morning sky. A mushroom cloud reached 40,000 feet, blowing out windows of civilian homes up to 100 miles away. When the cloud returned to Earth, it created a half-mile wide crater, metamorphosizing sand into glass. Oppenheimer, watching the fireball rise, recalled a line from Hindu scripture, "I am become death, the destroyer of worlds." The blast exceeded every prediction. General Leslie Groves and most of the scientists present had genuinely not known if it would work. That uncertainty, that terrifying margin of the unknown, is perhaps the most haunting detail of all. 3 weeks later, on August 6, 1945, a uranium bomb nicknamed Little Boy was dropped on Hiroshima. 3 days after that, a plutonium bomb named Fat Man fell on Nagasaki. About 210,000 people were killed in the blasts or succumbed to radiation sickness by the end of 1945. The human body, exposed to the thermal pulse of a nuclear detonation at close range, simply ceases to exist, vaporized in an instant. Those further away suffered burns covering their entire bodies, collapsed lungs from the pressure wave, ruptured eardrums, shattered bones. In the weeks and months that followed, radiation sickness moved through the surviving population like a second invisible bomb, attacking bone marrow, destroying white blood cells, causing hair to fall out in clumps, organs to hemorrhage, immune systems to collapse entirely. Survivors described a strange symptom that doctors could not initially explain, a burning thirst that no amount of water could satisfy, as the body's cells, irradiated and rupturing, screamed for hydration from the inside out. Japan surrendered unconditionally on August 15, 1945. The deadliest war in human history was over. If this story is already making you rethink everything you thought you knew about how the world works, hit that subscribe button right now, because every single week on Beautiful Mistakes HQ, we uncover the shocking accidental discoveries and hidden truths that changed history forever. You do not want to miss what is coming next. And Otto Hahn, sitting in captivity at a country house called Farmhouse in England, heard the news on the radio. He was on the brink of despair, as he felt that his discovery of nuclear fission led to the death and suffering of tens of thousands of innocent Japanese people. The man who had accidentally split the atom, who had simply been trying to create new chemical elements before Christmas in a Berlin laboratory 7 years earlier, sat alone in a room that night, overwhelmed with the weight of what his mistake had unleashed. He had not meant to build a weapon. He had not known he was standing at the edge of a new era when he submitted that paper. He had simply followed the science, step by careful step, into the abyss. The questions that remain are not purely historical.
Nuclear fission today powers approximately 10% of the world's electricity. The same chain reaction that vaporized Hiroshima heats homes, powers cities, and, in the view of many climate scientists, may be one of the only tools capable of decarbonizing the global energy system before it is too late. Lise Meitner, who declined an invitation to join the ManhattanProject and reportedly said she would have nothing to do with a bomb, spent the rest of her life grappling with the fact that her theoretical work had helped make it possible. She was nominated for the Nobel Prize 48 times and never received it, one of the most glaring omissions in the history of science. In 1997, element 109 of the periodic table was named Meitnerium in her honor. It is a radioactive element that barely exists, fleeting, unstable, vanishing almost the moment it is created. It is, in its own way, a perfect monument. There are still unanswered questions circling this discovery, like radiation around a reactor core. We do not fully understand the long-term genetic consequences of radiation exposure across generations. We do not know how close Nazi Germany's own atomic program truly came to success. Some historians believe it was further behind than feared. Others are not so sure. We do not know what Oppenheimer truly felt on the morning of the Trinity test when the light filled the desert sky. His words suggest awe and dread in equal measure. And we do not know, perhaps we will never know, whether a world that had never split the atom would be safer or more dangerous than the one we now inhabit. What we do know is this. On a cold December night in Berlin, a careful, methodical chemist fired neutrons at a uranium atom and expected to find something heavier on the other side. Instead, he found something smaller. And in that unexpected smallness, in that accidental fracture at the heart of matter, he found the force that had been sleeping inside the stars for 5 billion years, waiting for a curious hand to wake it. Otto Hahn did not set out to change the world. He set out to understand it. The world changed anyway. Some mistakes cannot be unmade. Some discoveries once made cannot be undiscovered. The atom split once is split forever. And the light from that first desert fireball, that blinding, beautiful, terrible light, is still traveling outward into the dark. If this story moved you, if it made you see the world differently even for a moment, share it with someone who needs to hear it. And if you are watching this and have not yet subscribed to Beautiful Mistakes HQ, do it now, because the next beautiful mistake we uncover might just be the most shocking one yet. Every discovery on this channel was once an accident. Every truth was once a secret, and we are just getting started.